Hello and welcome to CHeM In 3, the series where we spend no more than 333 seconds to consider 3 important points for the IB chemistry exam. Today on CHeM In 3, we look at Hess's Law. And for our 3 main lesson points, we will look at what is Hess's Law, why study it, and how to apply it. If A is converted to B, then the energy associated with this conversion would be the same if A were first converted to C and then C converted to B. The total energy change in a chemical reaction depends on the initial and final states and is independent of the reaction pathway. Suppose you wanted to find the amount of energy associated with this reaction, solid carbon plus hydrogen to form methane. You might think that this is quite simple, but the reaction leads to multiple products. So finding the enthalpy of formation in this reaction could be very complicated. But with a knowledge of Hess's law, it's possible to convert carbon to carbon dioxide, determining its enthalpy of combustion, doing the same with hydrogen to form water, and then to determine the enthalpy of combustion of methane, CH4. According to Hess's law, then the energy associated with this conversion and this conversion could be combined to solve for the enthalpy change associated with the formation of methane from carbon and hydrogen. This is the relevance of studying Hess's law. And while it is easy to understand Hess's law, solving the problems related to Hess's law in the IB chemistry exam can be just a bit more complicated. And it's important to follow a systematic procedure in solving these problems. Let's consider this question from the November 2009 exam, where we use this information to solve for the enthalpy change in this reaction. First, we begin by reversing 2 of the reactions that were provided to us, so that the desired reactant stays on this side of the equation and the desired product goes on to this side. But when you reverse, don't forget that the sign associated with the change must also be reversed. Next, we multiply this equation by 2. So everything on this side is multiplied by 2, and everything on this side is multiplied by 2, and the amount of energy is also multiplied by 2. Next, we cancel, looking at the molecules on this side, and where possible, if a similar number exists on this side, we can cancel this with this, aiming to leave only the reactant in the desired equation remaining after cancellation. Division can also be an option to help with this process. So let's cancel, divide, and solve. 7 oxygens here is cancelled by this 6 plus 1, 7. 4 carbon dioxides here cancels these 4 carbon dioxides. 2 plus 4, 6 waters cancel these 6. And what you're left with is C2H6 giving you 2H2 and 2C2H4. Because the equation that you desire is just C2H6 and not 2C2H6, then we take the sum of 1 plus 2 plus 3 and we divide it by 2. This answer would give us the enthalpy change associated with the given equation. And the answer comes to positive 137 kilojoules per mole. Now I would like you to try this problem from the chemistry handbook. Stop, try the problem, and then check your answer.